We'll be talking about network forensics analysis. I am Rami AlTalhi, incident response consultant at Cisco Talos. So we really, these days, APT attack have been leveraged the resources of the enterprise, private, and government sectors, and we need to have some detection capability against, the systems and to find out the compromised in the system. So let me move to the next slide. So as I said, we have, you can communicate with me using this email. So this email, you are welcome to communicate with me afterwards. So today's agenda actually is talking about a couple of bullet points here. We'll talk about the definition of network forensics. We got a very helpful definition from Wikipedia. We will discuss it in the next slide. And also talking about tools and platforms that you can utilize freely and available in the internet. We'll talk about network forensics challenges. The network forensics challenges has been expanded at the highest level we didn't see in the history. If you look into your traffic in your environment, for example, you will see the majority have been encrypted. There is no more Telnet, there is no more HTTP, which is a good thing, but it is a bad thing for the detection capability and the security control for monitoring systems. And we will talk about them. Also, we'll talk about how you can manage and contain that issues. Then we'll talk about handling huge Pcap by slicing. Maybe you've got huge Pcap data sets, sometime 200 GB or maybe more than that, and you need to look into that Pcap to find out where is the bad guys and what did they do in the systems. Well, once you use T-Shark, for example, the T-Shark will look into application layer, and you are not able to run or investigate huge Pcap in T-Shark. Sometime if you have normal systems, you need to have a memory equal to that Pcap, as it will be buffering into the memory to analyze those. We'll be talking about some tricks and tips for that and how you can utilize Wireshark for huge data set by splitting them over multiple pieces. Then you can merge them from the output that we got from this system. Then we'll be talk about some couple of scenarios for APT investigation use cases that are available and have been executed in the past. So what is network forensics? It's a sub-branch of digital forensics relating to monitoring and analysis of computer network traffic. This definition taken from Wikipedia, and I have seen this, one of the good definition about network forensics. In forensics, we have a couple of fields over there. We have host forensics, and we'll be talking about how we can combine both the host and network forensics together to get more valuable information and valuable investigation. So this is the majority of network data sources. We have a Pcap, the packet capture traces, and also we have a net flow. If you go to the customer side and you need to have some volatile data like Pcap or some DNS traffic to identify and find out what has happened in the past, you need a couple of data sources. Then we have a connection logs. It might be proxy, web, PC servers, etc. Then we have host artifacts like network sockets, SRAM, and we'll talk about it in the last during this lecture. So network socket can be grabbed from memory, can be grabbed from the system, the live system that you are working on. Also can be grabbed from the network equipment that you are investigating, such like router switches, firewalls. Here are a couple of tools and platforms that are available freely and open source and have very good community standpoint. We have Wireshark and T-Shark, and this is, become crucial to use and to understand their capabilities, anticipate them, where you need to investigate layer 3, layer 2, and layer 4 as well. Sometimes they have capability to investigate layer 7, like a DNS. And sometimes I think you can find out or filter based on HTTP some of the fields, but to boost your investigation up, you need to use T-Shark for investigating the application layer. Zeek, Snort, Suricata, those are fantastic tools. For Snort and Suricata for network signatures, and Zeek can parse application layer and provide you with the tons of information, such as TLS. When you parse TLS, you will have a lot of information out there. Network Miner also it provides visualized. Let's say it can visualize the Pcap itself and provide you with all parse information and user-friendly output. Unix-like utilities. What I mean by that is using Linux command line like grep, awk, and etc. Those we need to utilize at some time if you play with a T-Shark, as T-Shark can accept those by piping out to grep and awk and cut, etc. Archime, which is formerly Moloch, known by Moloch, to provide you a platform where you can ingest all the Pcaps that you have, and it make it searchable, and it's backed by Elasticsearch, and that means a lot of speed you'll get out of the system. Security Onion have a lot of resources and a lot of tools that we described here. It's already within the Security Onion. So having this system, it will be crucial, especially for if you set it up in your network or have some tactical purpose like responding to the incident. So enough talking about tools and platforms, and let's jump into network forensics challenges, where I can see this expanded more and more in the past and now and in future as well. The challenge that I think you will find it in most of the customers is having inventory assets. When you investigate a certain attack or certain incident, and you need to understand what has happened and to provide a recommendation and a plan or remediation, the customer itself should provide the inventory assets. And this is set in the first place if you look into CIS standards and security controls, as we will see in the next slide. So understanding the inventory asset should have, should be placed in the network and should have the right, let's say the right, should be written and should be understandable in the environment, so everyone can know where is these assets. For example, where is that system and this Windows system and that Linux server in the back end, and what's the IP, how it's communicating. These become crucial during investigation. Network baselining, we'll talk about how important is network baselining to identify abnormalities in the network. Also, we'll be talking about encryption, all sorts of encryption, TLS, SSH, RDB, and some other stuff. And the last challenge I can see is data source availability and usability. Sometimes you will have, let's say, specific data sources that is not available, like when you don't have the right log in the system or in the network, or you already have, but you are not using it, you are not transferring it to central utility like a SIEM, then this has become, a gap into your detection capabilities. So maintaining all of these can at least enhance your detection capabilities, and you can discover more and more techniques and attack types from the APT and other, attackers and adversity as well. So as we discussed earlier, inventory asset importance, you can see it here. It's set in the number 1. So number 1 in basic CI is controls. You see inventory and control hardware and assets, also the software. Having both of them in this priority, I think this will have much of understanding of your environment and how you can articulate your system to monitor them and prioritize them as well. The network baselining, as we can see here, let me just remove this a little bit. As you can see here, such incidents, you can see the spike here, for example, at 8th of January, we have a spike, and this can speak abnormalities. And to find those, you need to have a network baselining based on packet length or duration. Sometimes you can run payload entropy using the previously mentioned platforms like Zix Snort and Suricata. Also egress and ingress, looking into what is getting into your environment and getting out from an environment during a work day and weekend. This has become crucial, especially and looking into the holiday as well. Having the right baseline into the network will provide you at least the big picture about abnormalities and what should be, how you can handle those abnormalities in the network. It might be, happen during some changes in your environment, or happen during, some, you publish some services over there. So it can be understandable, but having, if you don't have, for example, the baselining, then we don't know what's happened and what is normal and abnormal over there. So network profiling. Now we need, this is actually to, overcome the encryption issues that we have. So we'll talk about J3 and J3S, which is, this set for TLS encryption. Also, we'll be talking about the JARM. Also, this is for TLS from server side. Then we're talking about hash and hash server to fingerprint SSH connections. Then we'll be talking about RDB, and as we know, the RDB is encrypted by TLS, and how we can get some useful information over the clear text transferred from client to the server. At the end, we're talking about community ID. So community ID to have, a single hash for the 5 tables, which is source, destination, IP, source, destination, port, also the transport protocol, which is TCP, UDP, SMB, and etc. So what is J3? J3, it's, MD5 hash value from TLS client hello packet. So this is actually from Salesforce team. They did awesome job to identify this algorithm. So what they did actually to, I fingerprint this to have TLS client hello, and based on that, there is some hash values over there. They based on and they got, the MD5 hash. So TLS version we have accepted ciphers, list of extensions, elliptic curve formats. All of these actually have been calculated based on the MD5, and it can be identify a single TLS client. As an example for this, let's say the attacker utilized the PowerShell from the system, and from the PowerShell they initiate a TLS connection to the command and control server. From the TLS connection, you get a J3 if you calculate it. And once you get that, you see, for example, this client is a PowerShell. The same thing, we will see another example for Tor. You can identify Tor with that. There are some caveats that we will talk about in the next slide for J3 and all other algorithm and fingerprint systems. So here we have added S. So J3S, it's maintained for server. in the same way as J3, but here we have a calculation just for TLS version accepted cipher, list of extensions from TLS server hello packets. So we have seen here Tor TLS profiling. So if there is a couple of sites that have a good data set for J3 fingerprint, you can just grab your J3 and just throw it in that side, and it will tell you what is the client is. And we have seen here the standard Tor client, mostly it's used by this MD5, and this the J3 server mostly by the second hash in this slide. Malicious TLS profiling, we can see, for example, TrickBot ransomware, and TrickBot usually use this hash, and from the server, the C2 and command and control server use this hash, the same way for Emotet. This slide, this is the search engine that you can just go j3er.com, just paste your J3 hash, then it will tell you what is the user agent or the client that initiate that TLS. Absolutely, there is, it's not exhaustive list, but at least you will have, some matches over there. If you, for example, calculate your current browser, either Firefox, Chrome, Microsoft Edge, whatever. Another search engine over there from abuse.ch, it's the same way, but it's add a tag to show you more information, like if this is a malicious, if it's malicious, okay, what type of malware families that belong to, and etc. We have seen here TrickBot, QuackBot, and some other ransomware J3 system, J3 fingerprint. So if you have J3, still there is a lot of work to identify TLS, because J3 can be impersonated, and it's not a good idea to just based on J3 you can say this is 100% it is generated from that client, because it is impersonated, and you can change the J3, and the attacker already did that, and they know how to do that. And we will show you an example how you can manipulate J3 from PowerShell, for example. So if you change the cipher suite or TLS version, this is will change J3 fingerprint accordingly. As we said, it's based on cipher suite, TLS version, and some other characteristics. If you change one of these, then you will have a different MD5. So what we can do, there is a couple of things that you can do. You can map it with other, let's say, artifacts from the host correlation as an example. Looking into Windows artifact, we will explain this in the last slide, like SRAM, that might provide you some conditions to evaluate over that. Also, other TLS characteristics and extensions as ALPN. So ALPN, before ALPN is maintained for tell you the TLS what it accepts as as protocol, or for example, tell you in HTTP 101 or in HTTP 2 and etc. So from those, browser actually have different ALPN characteristics, and output from those you can add profile to maintain your accuracy. TLS impersonation. If you enable, for example, TLS cipher suite from PowerShell and specify this cipher suite between quotation in here, and you are positioning them into this digit or any another digit, now we are providing it the lowest priority. Once you change the priority of the cipher suite, the J3 fingerprint will be changed accordingly. So attacker can do this, can do other things by different meaning or different means, but putting that in mind and having that in mind and correlating it with other characteristics will be very useful for your detection and to improve your and enhance the monitoring systems. Other limitation that we can talk about is the J3, as we said, it's not very unique for a single client. Sometimes you see attacker can utilize a legitimate system or legitimate application generating TLS by duplicating the same TLS characteristics to have, the same J3 as an example. So doing that, you will have a same and exact match for the MD5 value, where you can look at the search engine that we just shared previously. Then you see, oh, this is Chrome or Firefox. So ALPN, this actually, this image from Intop team, their website, you can see they identify actually two different example browser. We have Apple Safari, Google Chrome. You see in the below, we have a different supported version. You see, for example, we have LPN protocol and TLS supported version. Each browser usually provides you with the different values out of this. So you can profile TLS based on those values and extension, LPN extension. So now let's talk about SSH. I think there's a couple of questions over there. Okay. Yes, actually, this lecture will be available and recorded.
Yeah, they're just housekeeping, Rami.
Okay.
So just carry on.
So the hash and hash server, it's maintained for this research actually maintained by Salesforce team. They find out a way to fingerprint SSH without looking into the port. So it's port independent fingerprint kind of. If you look into this SSH handshakes, you see, for example, SSH message key exchange from these packets. So the client send a packet to the server will replies with the same message. So from just two these messages, we have hash and hash server. Hash based on the packet from the client, and the hash server based on the response from the server. So why do we care about those fingerprint? The first thing is to attribute the SSH connection with greater accuracy than only IP. Now you have more additional layer to identify the SSH connection other than just based on the IP. Once you got and parse any Pcap that have SSH connections with the script they maintain, the Salesforce in their GitHub repository, you'll have a value for those, SSH connection, one from client to the server and vice versa. So this has become very crucial and useful, as it will show you if there is any SSH and what kind of the client, even if it is behind the NAT device. If those devices behind NAT have a different clients communicating back to the C2, you will identify it without looking into the IP, which is, this is great stuff to have. During the investigation, usually you will have a couple of IPs, but those NATed IP, then you get just, stop and looking into different things and flow and etc. to identify those which became, very hard to complete the investigation. But having this parsed and available for you beforehand, and having those fingerprint, it will, provide you with tons of information about what's going on, also provide you with a client string, as we can see. It provide you with, let's say, it looks like HTTP user agent. If you use POTI, for example, if you use Xshell, if you use any other, for example, SSH from the Windows or SSH from Linux distribution, you will have a different, let's say, user agent alike to identify those systems. And we will see those in the next slide. So how the handshake happens. So we have a normal three-way handshake for the TCP. Then we have a server identification string and client identification string. And all of those became, crucial to identify the, as you can see here, we have OpenSSH from Ubuntu and we have OpenSSH from Raspberry Pi. The next thing we have to identify is SSH message key exchange from hash server and the hash itself from the client. Then, we have key exchange, then encrypted stuff from the command executed. So the key exchange, how it looks like in the Pcap, this is how we can see those in Pcap file from Wireshark. We can see some algorithm strings over there sent from client to the server. The same way we have from the server to client, we can see the set of algorithm, those generated from the server, and we can, have the fingerprint out of them using hash and hash server. So SSH client string. From the Pcap, we can identify those by looking into this packet. You can see below here, protocol SSH, OpenSSH from Windows. So once I did SSH connection from Windows CMD to the server, we have seen here, it's just printing the client name, like, HTTP user agent. And this is filterable. You can utilize the T-Shark to extract all of these strings and the client name and the server name, and have, you can have, full threat hunting based on the SSH based on those. So collecting those and parse them, you can utilize, I think, Zeek can extract them. So if you look into the Zeek and have, look into the SSH, you might get client and server strings where you can identify what's going on in your environment, who is communicating to who. Is this something usual happened, or something legitimate, something we need to block or protect, etc. So another thing that we need to look into it is SSH handshake as a covered channel. So covered channel is a way to place some information in unexpected fields. For example, in TLS, you can have some data into any extensions within TLS. But here, let's say you need to exfiltrate the data, and you can put some information into SSH message key exchange packet, and those actually will be traverse the network through the clear text. Once the attacker actually can code a malware to exfiltrate the sensitive data using those packets. It looks like, a DNS exfiltration, but it is for SSH. But and usually people looking into DNS and do not, have, a focus into SSH, especially for this packets. Then have fun getting those logs, since no one logged this packet, and no one parse those to look into what's going on. Once the attacker having all these messages into his backend or C2 infrastructure, what they can do, they can collect them, and parse them, decode them, and exploit them. It might be a document, it might be a sensitive data, secret stuff, traversing through this, SSH message key exchange. most of systems, and I think I have not seen until now any system can look into this SSH message key exchange and parse them, and can have a signature based on this packet. But it is doable and available. Like you can maintain snort rule and suricata rule and any other signature based for the network. Then you can actually look into it and see and understand what's the normal, abnormal, and apply your rules against those packets. So how we can detect those, as we discussed earlier, the anomaly detection is the way. So an anomaly detection, you can, for example, if you can see the client X communicating with server Y, but the client generating a different hash fingerprint into the server, let's say have tons of fingerprint coming out from the client to the server, that means something wrong with this client, since it just have a one let's say a one client generating all those encrypted messages. So the client should have a way to be persistent with SSH message key exchange, but not having a different clients generating a different key exchange messages. So looking into that, and the frequency of these will guide you into a proper detection methodology for this covered channel. So we just talked about J3. Also, we talked about SSH. Now it's the way to talk about the JARM, which is new methodology from Salesforce team to fingerprint the TLS from the server side. So it is really a fingerprint tool to profile the server running with TLS, and scanning with JARM provide you the ability to identify group malicious servers. What they mean by this is once you have, for example, a Cobalt Strike C2 running over TLS, JARM can identify that by fingerprinted. Also, JARM can identify a huge set of TLS running by the C2. There is no data set that I am aware of on the internet publicly available for the JARM fingerprint that you can search through it, like what we have seen for J3. But you can work in your environment and start profiling your environment based on the JARM and see if you can profile the legitimate services and legitimate TLS connections and baseline based on those fingerprint. Here's the repository for Salesforce team for the JARM. You can download it, you can run it into your own in your environment, and also you can automate that if you have a developed team. So why do we care about the JARM? Actually, it's a fantastic tool to quickly verify the server for the TLS. Also, to group the servers in the internet by the configuration. Once the TLS configuration changed based on the characteristics of JARM algorithm, you will have a different JARM fingerprint. So profiling the network based on those will be very beneficial. Looking, for example, into Google and YouTube, for example, and you start JARMing that, you will have usually a single JARM where it does tell us, this is become from the Google servers. The Salesforce team also the same. So you can even, group the TLS and their backend and where it's come from. So another way to look into the environment. So we can look into the AS number, autonomous system, or the IPs. Now we have a new way to look from the TLS standpoint, which is the jar. So we can identify the malware and command and control infrastructure and other malicious servers, as we discussed earlier, like TrickBot. You see some, you see some exfiltration through TLS that attacker utilized. You can also profile that, and you can share it with other teams. For example, if you have a miss, you can share that. If you have other, intelligence platform sharing, you can just share that with other team, and they can detect it immediately. So it become, a shareable information that and fantastic tool to share it with other team combined with GA3. There's an example. I have run the job, which is in Python language from their repository, and I have run it from my system to Salesforce team. Sorry, Salesforce.com. And you can see we got a jar fingerprint. Also, I have did that for Force.com, and you can see it is exactly the same jar fingerprint for both of them, which tell us this is, the same infrastructure TLS. Now, moving into Google and YouTube, we can see the same way as the Salesforce team, Salesforce.com. We can see two different hashes for the Google servers. So from this, I can say that it's, crown jewel to look into it in your environment and start, threat hunting based on the jar. So TLS didn't prevent us from investigation and didn't prevent us to threat hunt or do any compromise assessment as well. We can't share those, but it is still not accurate. Cobalt Strike, for example, have a jar similarities with Java 11 TLS. So there is, some false positive over there, and attacker can manipulate also the jar. The main thing is looking into a different data set, looking into different system, looking into different characteristics, looking into the timeline will unleash more information about the investigation. So if you break the jump rules, absolutely you will get another jump value. Iteration over server, TLS version and cipher suites can be automated. So you can automate actually, the TLS version. You can change the version between 1.2, 1.1, and 1.3, etc. to get a different job. And this is programmable, and you can do it in your own, and the attacker can do it as well. But looking into changing the techniques for the attacker, it will take time. And from the past, changing the techniques and the tools, it consumed a lot of effort for them. So usually they will use whatever works for them. So it's still very useful tool and fingerprint method to fingerprint your TLS. RDB. Now, as we know that RDB is TLS encrypted, but still RDB traversing some information in clear text, as we have seen in the SSH, where we can identify the client name and the server name the same way for RDB. We have seen here in Wireshark, we identified a field called cookie. So a field called cookie can show you the username for the one who's doing RDB. From the bottom, you can see the flow stream from the T-Shark testing. This is actually the user I did once I logged into the RDB. What we can benefit from that is having RDB looking into the cookie field, parse them, and Zeek already did that job. It will do it for you, and you can investigate it from the Zeek itself, or you can send those parsed data into your SIEM or any tools that you use, like Splunk. Then what you can do actually is looking into the frequency of the users. Are those legitimate users in your environment, or if there is any brute force against those systems from these users. Also, you can combine it with a source IP, and you can see a lot of stuff over there for RDB. So community ID. So community ID is the way to standardize the flow hashing. As we said earlier, based on the 5 tables, we can have a single hash that can be, let's say, can be shared with other entities or other customer or other, third party to identify if they do have the same flow from or into their network without leaking their 5 tables. So having the hash will provide you with the source IP, destination IP, source port, destination port, and the protocol without leaking them actually, since you have already the hash, which translated into the entire flow that you have. So there is no worry of the confidentiality if you have that hash and share it with other entities. Also, it will simplify the pivoting from different data sets. If you have a different data sets in your systems, you can simplify that by looking into just a single hash, and you can share it with internal team, and they will look into those data sets just by a single hash, a single value, not the entire flow looking like like 5 fields. It is not like looking into a single field, and analysts, I think they know that in depth. So Pcap slicing, we talked about huge, analyzing a huge Pcap. So sometime you will get if you work in as incident response, and you might have a huge Pcap like 500 GB or etc. And in this time, you need to slice it into the different species and look into a different characteristics for your investigation. So the packet slice can be based on the timeline. Once you get those huge Pcap datasets, you can get more information about what has happened and where actually where those events happened. And from the scoping call, for example, you can get more information about the timeline of the event, and you can set those timeline to grab all the Pcap files from those timeline. For the number of packets, you can split it over X amount of packets or protocol. If you have huge data sets and you are looking just for SSH, you can use TCP dump to filter out those through SSH and write it as an output and just focus on those. So out of 500 GB, for an example, you will get just, it might be 1 GB, which is very useful to look into. Source or destination IP. From the scoping call again, we have source and destination IPs. We need to look into them. We need to filter those from TCP dump, since TCP dump faster than T-Shark, as it doesn't look into the application layer. And now you can get just 2 tables of those conversations. So we have a single conversation out of these Pcap, and you are shortcutting your way into finding the root cause. The conversation, as we discussed, between 2 IP, or you can embed it with a TCP, which is more filtration, more or less amount of size for the Pcap. And anything filterable, you can look into your Pcap and think about it and see from the information you gathered from the event or the incident, and you can set your filtration over there and look into the Pcap and extract those from the Pcap. So slicing and merging, you can actually use a tool called EditCap. So EditCap, what it does actually, it will edit, and this is one of the packages that you will get once you install Wireshark application. Once you got that, you can slice and merge between the Pcap. Here you can, if I have or I know a specific timeline for the incident, you can run -A and -B, and we have now have a complete timeline in this format. Here's an example from EditCap. So I'm using here EditCap to filter from TCP to analyze a TCP analysis into different Pcap file using -C 1000. So you can do your filtration based on, based on the findings that you find from your analysis. Another way to do merging, there's a couple of ways to do merging. One of them using merge cap, and this is another executable or binary file you will get from the Wireshark. So now I want to merge, for example, between A and B Pcap into a single Pcap, which is output. So I will use -W output of Pcap, and this is the output of A and B Pcap. The same way we can do it with this example. You can have all the Pcap here and output it into single Pcap. Very easy. Now, another way to detect a threat in your Pcap file is using some network signature-based toolkit or framework. Here I'm using Snort, the same way you can use Suricata or other signature-based tool. And now I'm reading the file called the Pcap, and I have already a different configuration called snort.conf-l to show, if there is any matches with network signature that I have in my rules, Snort rules. So without looking into the Pcap itself, you can run your IDS, let's say. Since you already have the rules, you have an IDS to detect any maliciousness traffic in your Pcap just through running through Snort or Suricata. So let's move here. So we have a use cases. DNS over HTTPS malware. So some malware we'll talk about discovered by a team from Proofpoint. So Proofpoint did a fantastic job to identify some malware running over DNS for DNS over HTTPS. So what is DOH? DOH actually is DNS over HTTPS. You will see running into 443 TCP. Now this is made, the RFC actually made to enhance the privacy, and now that means the DNS will be traversing the environment and enterprises through HTTPS, which make it very difficult to identify the DNS callback to the C2. Now, querying DNS using HTTPS is the way for DOH. It's added more privacy, and a couple of browsers supported, like Firefox and Chrome. I think Firefox now supported by default, if I'm not mistaken. Previously, in the beta version was you need to configure it into your browser, and some malware now, coded their malware to use DNS over HTTPS using Google DNS servers, as we will see in the next slide. Now, adversary absolutely welcoming DOH as it's encrypt their callback into their command and control servers to hide from your security monitoring also your SOC analyst people. So Bsix Bot Malware is a malware that discovered or unleashed by Point. We can see from this malware, we have a two domain here encrypted or encoded. And once you decode it, you can see this domain, this weird domain, two weird domain over here. And the main thing is, which is in this rectangle, you see a web client request into dns.google.com. So attacker now utilizing Google DNS to have their DNS query run over HTTPS. From here, once you just do a get for that decoded DNS, you can see the response from the Google DNS, and it's provide you with IP which started with 119. So attacker used all the way, even the privacy implementation and security implementation, just to hide in the haystack and to hide from the security controls. So looking into those, it's became crucial, and we will discuss some point that you can monitor those requests in your environment as well. So another way to utilize DOH, not just to have or to run DNS query, it's by running or downloading a malware binary from the internet. Now attacker use there is a tool called DNSCat. So DNSCat was previously used to download, to exfiltrate data from the normal DNS, which is run over 53 UDP. But now we will see an example where attacker can do that through DOH. From this Pcap, actually, thanks for Leader Stephen for providing this Pcap. In this Pcap, we can see, actually, this is a decrypted HTTPS Pcap, but we will show you how that works. So you can look into, so I'm selecting here a TLS packet to show you how you can look into different characteristics in the Pcap. This is TLS 1.2, where the SNI or server name indication is traversed in clear text. And we can see here the server name dns.google.com. So this is absolutely a DNS request. This is not a normal TLS. Looking into that into your environment and filtering based on that, you can do it through the Zeek, you can do it with other platforms and technology that can understand the TLS extensions. It's become crucial, and you can filter based on that to look into who is in my environment doing DOH, and are they a user agent. And the cool stuff here is you can look into different things. So we discussed about J3, we discussed about the JARM. Now we talk about a server name indication. So by grouping all of these, you will have a fantastic visibility into your environment. So you will if you have J3, JARM, and etc., you will have the identification of the client and what they are using as a client. And then you can see also where are they going from the server name indication, and a lot of stuff over there. So still we can see stuff, we can identify them, we can also detect them in our monitoring tools. Here we can see this is actually the HTTP traffic decoded, but here just to show you the way the attacker did that. So now this is another way to look into DOH. Now we are looking into the host header from the HTTP, not from the TLS. We can see dns.google.com, and there is a link and below that indicate that this is a mimicat from that domain. So this is actually traversed through text record from the DNS. And here you can see how the attacker, let me move to the next slide. You can see, for example, here, the whole link, and we can see the response from the server, from the Google server. We can see the next rectangle and the below indicate that this is a basic C4 starting with TVQ. TV capital and Q small sometime indicate into MZ header. So MZ header in Windows binary means this is executable. And now we find that this actually a file, not a DNS request, and it is executable. So you can grab those, decode it into from base64 into an ASCII, and look into the binary and to see and to do also malware analysis against this binary. So very interested example Leader Steve did, and actually attacker can use it to to exfiltrate data, also to retrieve data from their C2 to execute stuff. So looking into this DOH is crucial and important in nowadays, especially for APT stuff. So last but not least, looking into SRAM as a network artifact. So what is SRAM? What is SRAM? So SRAM is abbreviated from System Resource Utilization Monitor. So it is one of the valuable artifacts for Windows OS. It's you can look it into a workstation. You can look into I think just remain 2 minutes, so I will be very fast for this. So you can look into the workstation. You can look into Windows Server. Both of them have the same artifact over, C Windows System 32 SRU. You will see that file there. You can parse it using different tools. You can find them from the GitHub, and very useful to map between binaries and the network usage. One of the investigation, I will share it with you here. This is an investigation I did for an attacker. He did, exfiltrate some data from the customer. And you can see the application name here. Here is a TS tunnel where he's tunneling back into his C2. We can see byte sent and byte received, and with associated with a timestamp. Looking into all of what we discussed over here will provide you phenomenal monitoring and understanding about what has happened, how we can look into Trojanized systems, and etc. So SRAM, fantastic tool, and a couple of people have a parcel for them. If you look into GitHub repositories, and can show you into for byte send received, you can map it with a Pcap. So this artifact from the network, not from the host. And here is a couple of references that used for this. Thank you very much for all, and looking into the questions.
Thank you, Rami. Yeah, there's a couple of questions there. Just one general housekeeping thing. People have been asking about the recordings. And I've been checking with Sherry and Angelo. They will be available within about a week, initially only for registered attendees for a period of time, and then they'll put them out to the public thereafter. We're just trying to work out how we do this with the virtual conferences, because even though we've generally recorded the live sessions when we're doing it in person, we all know that we get much more benefit from actually attending there and being there at the time and asking questions. So we felt that was the added benefit for attendees, but of course attendees on these virtual conferences have much less interaction with the presenters and everybody else. So we're just keeping it back for registered attendees initially. And so there's a couple of questions for you, Rami, there. One was about techniques for splitting large Pcaps, especially when you're creating very large filters because you're picking out a lot of items in it.
Yes, actually, I can answer that. So for this question, if you have a specified TCP port, for example, I have seen here in question is 1000 TCP conversation. I don't recommend looking into the T-Shark. I recommend using TCP dump, as TCP dump, it's very fast as it doesn't look and it's ignore totally the application layer. So the memory, your memory will be not utilized to dissect and to buffer those into the memory. So if you use TCP dump, let's say, and filter for TCP 8000, it will be very fast for you.
Yeah, I think it's just because you had a very large filter. Of course, if you're using a Wireshark display filter, it's got to dissect all that traffic and do a lot more with it. Whereas TCP dump just uses BPF capture type filters, which will run much faster. I don't know if there's a limit on the BPF filter size. But yes, that's a sticky one. Maybe Jasper would have some more info on that. His presentation, I think, follows this one where he's analyzing Megalodon files. These are the really big ones. So maybe a follow-up there. So couple of further questions there. Anything like SRAM for Unix?
Actually, SRAM is specified for Windows as it's look into resources for the Windows with executables. I'm not aware if there is any SRAM. I don't think so, but you might. I will recommend to use audit daemon from the Linux with the right rules. You might get a good monitoring over the Linux using audit D.
Yeah, I found that I'd never heard of SRAM before, but it looks very interesting. That's a persisted database over a long period of time, which is very helpful for going back into the past when you're doing analysis. And then another question here about seeing those hashes such as JAM and Wireshark itself. That occurred to me as well when I was seeing that. Again, this was new to me, JAM and JAM3 and so on. And I think it's probably a good idea. Wireshark could display those hashes itself, and then you would be able to filter on them. So somebody should raise an enhancement issue over at Wireshark's GitLab site where we could think about adding that. Let me just pass a link here. So I'll just put it in the chat. That's where you raise Wireshark issues, and that's open to anybody. Anybody has an issue, whether it's a problem or enhancement, put it into the GitLab site there, and then we're not going to forget about it. It's all very well asking us to do something at a conference, but we are so excited at meeting you all that we suddenly forget those things. So sticking them on the GitLab issues site.
For this question, I have seen, I think, the J3 being written for the Wireshark, and the same way I think it can be written if you just use maybe Lua, but as Graham said, we can have this as an idea for GitLab link that he shared.
Yeah, you could do it with a Lua post dissector, but of course then if you've got very large capture files, then you've run into the slowness of Lua or relative slowness of Lua. But I think it'd be a good idea for Wireshark to certainly add some of those hashes there, and then you'll be able to filter on them. David says, can you go back one slide to your references page? So you'd like to copy your references. And any other recommendations for SOC operations when dealing with encrypted traffic?
Yes. We discussed about fingerprinting for TLS, also for SSH, hash cipher and hash, also the JARM. If you use a platform like a Zeek and integrated with your system, at least you send those fingerprint to your system and make it searchable. It will be, very useful for you. So yes.
And then one from Chris Maynard, another core developer, just pointing out that you don't really compare TCP dump to T-Shark because, as we discussed in that answer there, T-Shark will try and do a full dissection. So dump cap is the Wireshark equivalent to TCP dump. So that's available with the Wireshark suite. So dump cap will do just BPF filtering and won't do full dissection. Okay. So I think I can click the buttons on all these. And any other questions from anybody? There was one from Samantha there. If you can't decrypt DOH traffic, can you try and use the response size as an indicator? Or are there any other indicators that you can acquire from encrypted traffic?
Well, if you're talking about the environment itself, you can enforce, TLS decryption, for example, to even assess your IDS. If you have IDS, you need to pass those DOH into those IDSs as well. So an environment is totally different when we talk about working from home, if it's not connected to the enterprise like shadow PCs. But yes, you can do that by enforcing a TLS certificate for the domain for your enterprise.
So you're saying we really got to do DPI.
Exactly, yeah.
I think the question really was, is that are there any other IOCs that could be just available with the encrypted traffic? I mean, obviously we have the hashes that you've talked about, but
it's different when you look into TLS 1.2 or 1.3. 1.2, at least you have SNI over there. With J3, you can combine both of them to have a useful information. But once you have 1.3, you just have the normal fingerprint like J3, JAM, etc. So TLS 1.3 is a pain for monitoring. Looking into the response size might unleash something. I didn't do that really, and it might be a good for AI research or for big data and look into those traffic.
And of course, if the bad actors have got any sort of crypto knowledge, then they'll pad the packets to make the length irrelevant. So it's very difficult to ascertain anything from actual packet size. So really, DPI is the only way to go if you're really looking to see inside that TLS data.